Hey there, I'm Nix, and today's video is solving the find all numbers disappeared in an array problem on the LeetCode website. As always, solving this problem in C++ and giving you a detailed explanation of the entire process, through the planning of the algorithm, to the coding of it, to the analysis of time and space complexity, as well as looking at the LeetCode rankings. If that sounds good to you, then stay tuned. Welcome back. Let's get to solving the last problem in this Array 101 card. We're given an array nums of n integers, where nums I is in the range of 1 to n. So in other words, we can't have an array that has, say, 3 integers present in it, and one of them equals 5. The values have to be between 1 and n. So we want to return an array of all of the integers in the range 1 to n that do not appear in nums. So as this example shows, we have an array that consists of a range of 1 to 8, and thus 8 numbers. But we have 2 appearing twice, and we have 3 appearing twice, and 5 and 6 do not appear at all. So our output is going to be an array that consists of the values 5 and 6. Same story here. We have an array that consists of 2 numbers, but both of them are 1, so we output 2. Looking at constraints, nothing immediately comes to mind. We're never going to be able to be given an empty array. The follow-up, however, is very interesting. Could you solve this problem without extra space and an O of n runtime? That's going to be the focus of the second solution I'll show. But the first solution is just going to focus on solving it in any way possible, not worrying about optimizing space and time. Now, a way to do that fairly easily is by, well, using additional space. If you make additional vectors, additional arrays, then this problem is fairly easy to handle. So let's take this example here again. If you go through it and you make another array that will house the count of how many times you see a value, which includes 0 as a default for the entire range here. So you're going to increment up from 0 to 1 the first time you see a number. If you see it again, it'll increment from 1 to 2, and so on and so forth. But if you never see a value, it's going to keep its default count of 0. So this array is going to create a count array that looks like this, where you see the value 1 once, so the first number in the count array is 1. You see 2 twice, so that's the second value has a count of 2, and so on and so forth. But 5 and 6 do not show up, so the 5th and the 6th numbers in this count array show 0. From that count array, if you iterate through that, and every time you see a count of 0, you can add that index plus 1 to a new array that will house the missing values, and only those missing values. Once you've gone through that count array, you can simply return that array that you've created. So with that plan, let's move on to actually coding that out. First up is creating the 2 vectors that I described. One of the vectors is going to house the count of all of the values. I set that's equal to a size that equals the nums array, and it's just filled with zeros as a default. The next vector is going to house the missing values. The next thing to do is to make a for loop and go through the nums array from the beginning of it to the end of it and count up the values that we see. So in this example here, this is the nums array that we're given. Via this line here, this is how the count values array initially looks. And we now go through this array and count all the values. So the first value that we see, nums I, at the starting index of 0, is 2. We subtract 1 from that, 2 minus 1, 1. So at index position 1 in the count values array, we want to increment that value up. So 0 at index 1 goes up to 1. Now we move on. We see a value of 1 when in the index goes up to 1, and 1 minus 1 at index 0, the value of the count array is going to increase, so this goes up. And finally, we see 2 again. 2 minus 1, index 1, we increment the count up, so we now go from 1 to 2. So we've seen 1 once, we've seen 2 twice, and we've seen 3 a grand total of 0 times. The next for loop is going to go through the count values array from its beginning to its end, and every time you see a value present in that array that equals 0, you're going to add the index that you're at plus 1 to the missing values array by calling the pushback function. So we go through the count array. That's not a 0, that's not a 0. Ah! That's a 0. So now we are at index 2 here. Now at index 2, we add 1 to it. So 2 plus 1 is 3. We add 3 to the missing values array, which plonks it right there. The final thing to do is, now that we've filled in all the values that are relevant for the missing values array, we just want to return that missing values array too. Going through the example, no bugs showed up. The logic seems to work as I think it should, so this should be able to handle everything. Now let's prove that and run the code. And we should pass. Good. 5, 6, 5, 6. Now let's submit. Pending, judging, and green text. Lovely. Before we hit the button here, let's go over and do some time and space complexity analysis. For space complexity, we've created these 2 vectors here. One of them is dictated by the size of the nums array, and it will exactly equal it. This one, however, its size will be dictated by how many values are not present in the original array, and we can call that a different variable. So this algorithm will have a time complexity of big O of n, where n is the size of the original array, plus m, where m is the number of values that are not present in nums. And I count everything here because I'm not going under the assumption that the returned list just doesn't count. I count everything that takes up space, even if it would be temporarily. So I count everything. So this one would be big O of n plus m. In terms of time complexity, we have a for loop here is dictated by the size of nums, doing constant time work. This one also essentially is dictated by the size of the nums array, because the count values array is exactly the same size as nums. So you can just call those both n. But you use the pushback function here. The pushback function in C++ does, for vectors, does have an amortized constant time complexity. The for loops both are dictated by n, and this, instead of being like purely constant, would be amortized constant. So I would say that these would have an amortized big O of n time complexity. So let's look at the rankings now. Okay, fairly big range for the runtime. These are probably answers that have higher time complexities, big O of n log n, maybe big O of n squared. But this distribution here probably houses the various types of big O of n solutions. And we're within this distribution, so pretty good. And we would probably, as always, ping pong within these range. If you have a big O of n solution, you'd probably ping pong around this distribution. If you have n squared or log n's, you'd probably ping pong around that relevant distribution. Okay. Wow, this is a large memory range. We're here, which makes sense because we aren't optimizing our memory usage. We did have to take extra space as a result. Here, we're not in solutions that have larger complexities that are represented down here, but neither are we within some distribution of this highest one, which is probably ones that do in-place solutions as a result. So our goal is in the second solution that we're now moving on to get somewhere into this distribution and maintain our time complexity distribution, you are here sign, being somewhere in this range. So that's the goal. With solution 1 done, let's move on to creating solution 2. And solution 2 is going to be our in-place solution. To do an in-place solution, we need to find some way of altering the array in such a way that we can record what is present by marking the numbers in some way, and then we can use that information in subsequent parts of the algorithm to make further modifications to ultimately get to what we want. An array that consists only of what was missing in the original. But that leads to the question of how are we going to alter it? Well, for instance, looking here, first number you see is a 4. Well, if you see a 4, it exists in the array, and thus perhaps you can alter the number that exists at the 4th position in the array in such a way as to mark it. So at the end of that process, numbers that exist in the array will have numbers that are present in their corresponding position value marked in some way. Numbers that don't exist in the array will have values that exist at their corresponding position numbers remain untouched. So we see a 4 here. We want to mark 7, the number that exists in the 4th position, in such a way that we can record that, hey, we saw 4, so position 4 gets marked. But we have to do that in a very specific way or we're going to lose information. For example, you can't say, oh, well, I'll just turn everything that I see into 0. Because 0 is not a possibility to be seen in the array. But if you do that, you're now no longer going to register that 7 was in the array when you get to this point. You start here, you're going to alter 7 and turn it into a 0, so that once you loop into the array further and get to that position, you're now just going to see a 0 and you're never going to know that 7 was initially present in the array in the first place. So you still need to maintain the value, but you need to mark it. And the way to do that is by turning the value that you see into its negative. So 7 here is going to become negative 7. That way, you still have the magnitude of the number, and you can still be able to use that value to mark indexes once you get there. So that's the first part of the algorithm. Now, after we do that, we're going to have to go through that new modified array and suss out that information. So we're going to look for the unchanged positive values, and the positions that those positive values are at, we're going to make sure to alter the numbers at the front of the array into those position values. So in other words, when we go through this array, we're going to see the 5th and the 6th positions still be positive. So 5 and 6 are going to be the numbers that replace the first 2 numbers in the array. So we're going to have 5, 6, and then the rest of that modified array. After that for loop occurs, which is the second step, our third major step is going to be getting rid of the junk that we don't want in the array. We only want 5 and 6, not 5, 6, and whatever else. So, to do that, we can make use of the resize function that comes with the vector class. And that resize function will ensure that the array gets adjusted down to house only those numbers that were not present initially, and it'll delete everything else that may exist beyond that. So, at the end of those 2 loops and the resize function, we're going to have an array that just consists of what we want. And then the final thing to do is to just simply return nums that's been altered to that point. So with that brief overview of the major parts, we're going to move on to the coding aspect and then use this example and walk through it via the code to understand what the code is doing at every step. This is the beginnings of the first part of the algorithm. And as you can see by the wall of blue text, it's mostly comments at this stage. But this is the for loop that's going to turn the relevant numbers negative in the array as a way to record what values are present. And in this situation, we could see one of 4 potential situations play out. The first of which is that the value and the position target are both positive. So here we see 4. 4 is positive. And then that leads us to our position target of the value that's present at the 4th position, which would be index 3. Here is a 7. So we want to turn that positive 7 into a negative 7. The same scenario occurs when we move on to 3 here. 3 is positive. We look at the 3rd number in the array at index 2, and we see it's also positive. Well, that won't do, so we turn it negative. Now when we get to here, however, the second scenario plays out. This time we're seeing a value that's negative, but our position target, since this is 2, it points to the second number in the array. We still need to turn that target into a negative value. As we move further into the array, we will see situation 3 and 4 play out. So we were here, did the alteration, we move on, we see negative 7. We essentially need that to mean that it points to the 7th number in the array. We turn that negative. Move on to 8, turn the 8th number in the array negative. Now we get to scenario 3 here, where we see a positive value, but it points to something that's already been altered, something that is already negative. In this case, we don't need to do anything. And the very next thing we come across is the final scenario, where the value is negative and its position target is also negative. Again, in this scenario, since our position target is negative, we don't need to do anything. And since both of these scenarios, we don't actually need to make any alterations, these scenarios essentially don't need any code, so they go bye-bye. The only 2 scenarios we need to write code for are these 2, because it's these 2 situations that we actually need to do something, aka turn our position target from positive to negative. This if statement is going to handle this first scenario. Condition, we want to look at the value and make sure it's above 0, and we want to take that value, we want to subtract by 1, and we want to take that index value, look at the number that's present in that position, and want to see if that number is also positive. If both of those conditions are true, then we want to take that position target and set it equal to the negative of itself. The else if condition here is going to handle the situation when the starting value is negative. If we leave the starting value negative, then because that is being used to reference indexes, if we leave it negative, it's going to end up with a negative index. That's going to result in an out of bounds error. So we need to first turn that negative value into a positive in our referencing to ensure our index is always positive. So if the condition of the value is negative, less than 0, and we need to turn this number back into a positive number by taking its negative. Negative and negative value turns it back into a positive. So this, in this situation, nums_i would be -2. -2 turns it back to +2. 2 minus 1, we get a positive index value. The same thing essentially needs to happen in the actual code line within the if statement. We need to make sure in our referencing of nums_i, we take its negative instead to ensure it's ultimately a positive value that gives us a positive index. And then we essentially do the same thing. We turn this entire value here, the position target, into its negative. Step 2 is going to be handled by this for loop. And this for loop should look very, very familiar because this code has cropped up in several other problems. This section is going to handle turning this altered array, which houses all of the negative and positive values, into an array which actually houses the values that were not present and puts those values in front. The way it does this is we need to create one integer variable, and it's going to go through the array from the beginning to the end. And if the number is negative, it's going to count that and store it in this variable. If it runs into a positive value, however, it's going to set the value in the nums array at the position that's equal to index minus negative count. And it's going to set that value equal to the index plus 1. So it's going to turn this array, which is the result of this for loop going through the original array, and it's going to go and count the negative values. Okay, we start at the beginning here. We see 1 negative, 2, 3, 4. All right, and then we see a positive number at the index of 4. So we're at index 4 here. We see a positive value. Now this else statement comes into play. So we want to set this value at index of 4 minus our current negative count. And at this stage, we've seen 4 negative values. So index 4 minus 4 is 0. So at the very start of the array at index 0, we want to set the value of that position in the array to equal our index 4 plus 1, which is 5. So this will turn negative 4 into 5. Same thing happens for the second positive value. Again, at that stage, we have seen a count of 4 negative values. We're at the index of 5 now. So at 5 minus 4, index 1, which is here, we're going to turn that value so that it equals 5 plus 1, or 6. Then it's going to continue on and see this negative value, which ups the count to 5, and finally this negative value, which ups our negative count to a total of 6. So this is the alteration that happens for this section of code. Third step, to delete all of this other stuff that we don't want present in the array. And we do that by calling the resize function. So nums.resize. And then we want to tell it, well, how big is the array that you want to create? In this situation, the array that we want as our final size is always going to be equal to the original size minus the negative count. So in this example here, our initial size was 8, and 6 of the values ended up turning negative. So our negative count was 6. 8 minus 6 is 2. There were 2 missing values. 2 is the size that we want our modified array to be, and thus it'll delete everything past that and preserve the first 2 things present in the array, which is why in this step we made sure to put those altered values, the values that were not present, up front. Last but not least is to return the nums array that we were given in the first place. So going through all of that, the code should work. There shouldn't be any bugs. Please, 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 no bugs. Finished. Okay, 5, 6, 5, 6. This is good. Submit. Judgment. Green text! Woohoo! Yay! Alright. With and accepted, let's turn to time and space complexity before we look at our rankings. So as you can see, the only variable that I had to create and thus carve out space and memory for is this negative count variable. And that negative count, being an integer, takes up constant space. Since it takes up constant space, the entire algorithm here is going to equal a big O of 1 space complexity. It is an in-place algorithm to accomplish the goal. So that is definitely a big improvement over solution 1. Now looking at the time complexity for this, we've got a for loop here. It's doing nothing but constant work, and it depends on the size of the input array. Similar story in this for loop. It again goes through the entire array, and it's again just doing nothing but constant work. Now looking at the resize function. The resize function also has a linear time complexity dependency. Now you might have been wondering, well, if you just want to erase these junk values from the array, why couldn't you just call erase? Well, yeah, that would work, but if you're calling the erase function from within a for loop, that's not going to give you big O of n time, because the erase function itself has linear time dependency. And if that's embedded within a for loop that also has linear time dependency, you're going to have a multiplicative effect on the time dependency, and it's going to be akin to an n squared dependency. So that's why I couldn't use the erase function within a for loop. To get around that, I can use a resize function. The resize function also has linear dependency, but I don't need to call it from within a for loop. So this essentially just, in terms of time complexity, functions like another for loop. It has linear time, this has linear time, this has linear time. So the entire algorithm has a big O of n time complexity. And with that, we have achieved the follow-up. Doing it without any extra space at all, a truly in-place solution, and doing it in big O of n runtime. With that, let's look at the details, and hopefully we're still in that first big hill of the runtime, and we're hopefully within that big first hill in the memory usage as well. So let's see if we've achieved that. Yes! We're still present in this hill here. And we are also present at the very top section here in this memory usage, which again makes perfect sense because it's an in-place solution. That was how to solve the find all numbers disappeared in an array problem. I hope you got something useful out of this video, and as always, I will wish you happy coding and to have a nice day.